Okay, let's try something different. Kind of tried this before, but yeah, I'll do it again. We used the new chat thing in GPT-4 or whatever it's called. Yeah, do we need a prompt to begin with? Just see how we go. I think we only have 1 hour or something. Okay, can you give... so you know what the BioniChaos is that correct?
Yep.
That's good.
Got it.
Okay, do we have something on PPG? Do you know what PPG is?
Yep.
So we should have a page on PPG on the website, but currently it's just a blog.
Got it. If you'd like to expand it, you could turn that blog into a comprehensive resource, maybe by adding interactive elements, visualizations, or even a simple tool for users to explore PPG data. This could make the page more engaging and informative.
Well, yeah, that's exactly what we want to do. That's a great idea.
Perfect. Incorporating those elements could really elevate the user experience. Is there a particular tool or visualization you're thinking of adding to the PPG page?
So generally, we would like to make sure first that it's super realistic. So we want to rely on
Got it.
yeah, I want to rely on well, maybe not real data, but yeah, there's this there should be papers on how PPG should look like.
That makes sense. Referring to scientific papers can provide you with accurate baselines for realistic PPG waveforms.
Yeah,
You
okay.
can use this information to create simulations or visualizations that closely mimic real-world PPG data, ensuring a high level of realism.
Yeah, okay, that sounds good. Just moving forward, if we can do rapid fire
Yep.
responses, yeah, and don't interrupt if I'm when I'm talking. That would be great. Anyhow, yeah, we want to move forward. So can you give suggestions for a PPG application? So we're thinking a synthetic data visualizer, so we can learn about PPG, showing all the necessary components in it, things like that. Just a quick response.
Sure. For a PPG application, you could create a synthetic data visualizer that educates users on PPG signals. Include components like heart rate, blood oxygen levels, and pulse waveforms. Users could interact with the data, learning how different factors affect PPG readings. This
Yes,
interactive approach.
yep. Sounds good. We want quick responses, please. Like if we can speak a bit faster and shorter responses, that would be great. We're doing like a rapid fire, and then we get to development later. Yes, we would like to focus on the waveform itself.
Got it. For a focus on the waveform, your PPG app could let users manipulate variables like heart rate or blood oxygen levels and see real-time changes in the waveform. This hands-on approach would help users understand the dynamics of PPG signals.
Yeah, so how many variables are there in the PPG waveform? Quick response.
There are typically several key variables: heart rate, blood oxygen saturation, pulse amplitude, and sometimes pulse transit time. These can be influenced by factors like blood volume changes and vascular health.
Yeah, that sounds good. So, how do we go about developing an application? I'm thinking just HTML and JavaScript.
For an HTML and JavaScript app, you'd start by designing a simple, user-friendly interface. Use JavaScript to generate and manipulate the PPG waveform based on user inputs. Libraries like D3JS could help with data visualization. You'd also incorporate interactive elements, allowing users to modify variables and see real-time changes in the waveform. Hey, I'm ready to hit the ground running. So if there's any...
Okay, that sounds good.
Great! It sounds like a solid plan for an engaging and
Yeah,
educational
can you keep
PPG app.
short responses? Can you go back to just saying yep when I'm not asking a question?
Yep.
That's good. Yeah, forgot to say yep.
Got it.
Okay. So yeah, so
Yep.
thinking opening so we'll be using Canvas GPT-4o. I wonder
Yep.
if I can open
Yep.
the chat. Well, yeah, that's the chat that we are having.
Yep.
Yeah, can you give some quick options for naming the web application? I need a title, but also a short name with no spaces in it for the URL.
For a PPG web app, how about the title Pulse Vision and the short name Pulse Viz for the URL? It's catchy and reflects the app's focus.
Okay, that sounds good. Yes, we do pulse viz. Sounds good.
Great choice.
But then, okay, so we would like prompts for for another developer to do all the coding
Sure. What
in.
kind of prompts are you thinking of for the other developer? Are you looking for coding tasks, design ideas, or something else?
No, what we're talking about is we're staying on topic. We'll just like a PPG visualization, a synthetic generator and visualizer application just made in HTML and JavaScript. Can you provide all the necessary prompts for another developer to do the coding from scratch?
Got it. Here's a set of prompts to guide development. 1. Design the UI. Create a clean, intuitive interface using HTML and CSS, focusing on a central canvas for waveform visualization and controls for adjusting variables like heart rate and oxygen levels. 2. Waveform generation. Implement a JavaScript function to generate synthetic PPG waveforms. This should allow for real-time adjustments based on user input. 3. Interactivity. Add interactive controls for users to manipulate variables and see instant changes in the waveform. 4. Data visualization. Use D3JS or a similar library to enhance the visualization of the PPG waveform, making it more engaging. 5. Educational elements. Incorporate tooltips or overlays that explain different aspects of the waveform and what changes in variables mean. 6. Responsiveness. Ensure the application is responsive and works well on various devices. 7. Testing. Plan for thorough testing, focusing on usability and accuracy of the waveform generation. These prompts should help guide the development of your synthetic PPG visualizer.
Hey, can you also give the a one paragraph overview of what the application is?
Sure, the application Pulse Vision is a web-based tool designed to simulate and visualize synthetic photoplethysmography PPG waveforms. Using a user-friendly interface, it allows users to adjust variables such as heart rate and blood oxygen levels, instantly reflecting these changes in the waveform. The app serves as an educational platform, showcasing the dynamics of PPG signals through interactive, real-time visualizations, making it ideal for both learning and demonstration purposes.
Okay, let's close that for a sec. I think we got what we need for now. Let's see if it will start a canvas. Probably not. Should in theory start a canvas after this prompt.
These prompts are a clear and effective roadmap for developing Pulse Vision. Here's a bit of elaboration to help focus each phase even further. 1. Design the UI. Start by sketching a minimalistic layout that emphasizes usability. Consider placing a large canvas area centrally for the waveform display, with sliders or dials positioned below or to the side for adjusting heart rate and oxygen levels. Maintain a consistent color palette to ensure a professional look and help highlight important elements like changes in waveform characteristics. 2. Waveform generation. For generating synthetic PPG signals, you could define a base sine wave and modulate it based on user input to represent heart rate and oxygen saturation. JavaScript can provide the real-time calculations and updates, and this could be a good place to explore adding subtle noise or irregularities to make the waveform look more realistic. 3. Interactivity. Using HTML input elements such as sliders, you could easily add real-time control to modify heart rate or oxygen levels. JavaScript event listeners will be key here, listening for changes and immediately recalculating the waveform. 4. Data visualization. Leveraging D3.js is a great idea for bringing these waveforms to life. D3 will allow you to smoothly animate the waveform and offer transitions that enhance user understanding of how the changes propagate. It can also help in adding contextual information, such as thresholds for normal versus abnormal heart rates. 5. Educational elements. Adding tooltips that appear when users hover over specific features of the waveform could significantly improve the educational value of the app. These tooltips could explain how features such as the systolic and
Okay, can we generate all the instructions, all the prompts necessary in the text canvas, in a new text canvas, all the detailed prompts for the entire application, making sure only HTML and JavaScript and CSS is used. I don't particularly mind which data visualization tool is being utilized, as long as it looks good. Yeah, would love for it to be interactive and realistic. We are looking at synthetic data generation and visualization as described. This should start a new canvas. Yep, so this is a text. Can you do it without any code, just text alone? Text alone. Just gonna, yeah, so generating from scratch, that's nice. So we have the user interface, waveform generation, interactive and real-time feedback, visualization of JavaScript, tooltips, responsiveness, cross-device compatibility, testing and feedback, final touches. Okay. Okay, that sounds good. So now based on these instructions, can we start another canvas? Another canvas with a second canvas which will have the HTML code template in it. What? Another. Cannot get, yeah. Another canvas. Okay, I think it will, I think you understand what I mean. Just confirm. Can't be bothered correcting the text, but I expect. Yep, second canvas with a HTML.
I've created a new canvas with a basic HTML template for the Pulse Vision application. This includes the initial structure for the canvas and controls, such as sliders for heart rate and oxygen levels, as described. Let me know.
Okay, can we change it to actually include the JavaScript as well, embedded within the HTML code? Can you modify the current code accordingly? Can you also specify what else do we need? The code currently seems way too short. We might need the styling as well. Styling. Cannot understand my voice today. I don't know what's up. Okay, we have a bit of a CSS there. We have the script. Okay, we have 4 sliders for heart rate, oxygen level. Wait, is it? Can you explain the sliders in the chat alone without changing the code?
The sliders in this code are used to adjust two key variables, heart rate and oxygen saturation, which influence the waveform displayed on the canvas in real time. 1. Heart rate slider. Heart rate slider. This slider allows users to modify the heart rate value represented in beats per minute, BPM. The range is set between 40 BPM and 180 BPM, with an initial default value of 80 BPM. Whenever the slider is moved, an event listener updates the heart rate variable and adjusts the displayed BPM value, heart rate value. Changes in heart rate directly affect the frequency of the synthetic PPG waveform drawn on the canvas, simulating the effect of a faster or slower heartbeat. Up 2. Oxygen saturation slider, oxygen level slider. This slider enables users to adjust the oxygen saturation level, shown as a percentage. The value ranges from 85% to 100%, with an initial value set at Totstar 98%. Like the heart rate slider, an event listener updates the oxygen level variable and adjusts the displayed oxygen level value. Changes in the oxygen saturation value impact the amplitude of the waveform, reflecting the effect of varying blood oxygen levels on the PPG signal. Both sliders are implemented using the input type range element, and they are.
Okay, so how do we make it look more like a real PPG waveform? Hey, can you just explain first without changing the code? Did we have it in? So we have another canvas. You have the development guide, waveform generation.
Sure, the application Pulse Vision is a web-based tool designed to make the synthetic PPG waveform look more like a real PPG signal, we need to introduce a few key characteristics that are typical of an actual PPG waveform. Here are some suggestions. 1. Waveform shape. The current waveform is purely sinusoidal, but an actual PPG waveform has a more complex shape. It features distinct peaks and valleys that are not perfectly sinusoidal. To simulate a more realistic PPG waveform, you could use a combination of functions, e.g. sine and Gaussian functions, to create multiple components: the systolic peak, the dichrotic notch, and the diastolic wave. For example, the systolic peak can be represented as a rapid increase followed by a slower decay, while the dichrotic notch appears as a small dip after the peak. 2. Simulate cardiac cycle features. In a typical PPG, the systolic upstroke, a sharp rise, is followed by a dichrotic notch and a dichrotic wave. To mimic this, you can combine a sharp increase with a smaller secondary peak. This can be accomplished by using custom mathematical functions for different phases of the cardiac cycle. Add segments to your code that calculate a sharp rise followed by an asymmetrical descent, which would be more representative of the heart pumping blood and the recoil in arteries. 3. Introduce physiological variability. In real PPG signals, there is a natural variability between beats. You can introduce some random noise to simulate this variability. For example, add small random fluctuations to both amplitude and frequency to simulate slight changes in heart activity and breathing. Use a random number generator to slightly modify the timing, time, and amplitude parameters in the waveform drawing function. This will give it a more organic and less robotic appearance. Number 4, modulate based on heart rate. Instead of directly using a simple sine wave whose frequency corresponds to the heart rate, consider adding nonlinear scaling so that the waveform appears more like an actual PPG at different heart rates. At higher heart rates, the waveform should become slightly shorter and sharper, reflecting the reduced time the heart has for filling and ejection. 5. Add small secondary features. Include a dichrotic notch by adding a small decrease in amplitude after the main systolic peak, followed by a secondary smaller wave. This can be done by defining different phases within a single heartbeat and combining them into the final waveform. This secondary feature can be added using a smaller sine or Gaussian-like bump following the main peak. 6. Styling and visual improvements. Modify the line thickness and color based on the physiological parameter inputs. For example, a lower oxygen saturation could be visualized as a redder waveform line, while a healthy oxygen level remains blue. Consider
Yeah, so it sounds like you know quite a bit about what a realistic PPG waveform should look like. So that sounds really good. So can we keep everything as is at the moment with the code? And can you write the, so essentially we want to change the current web application to essentially have another set of separate set of controllers at the bottom of the page that will control all these 7 items that you mentioned. So the waveform shape, yeah, so can we cover the waveform shape? Can we add controllers for changing the waveform shape? We want to get it right. We want to make sure it looks more realistic, but still correct based on literature. So yeah, if you can leave the code as is and add extra features for making the waveform shape more realistic. Can we do that?
I've added a new set of controls to modify the waveform shape, including sliders for waveform sharpness, noise level, and dichrotic notch intensity. These adjustments should help in creating a more realistic PPG waveform, allowing fine-tuning of the waveform features to better simulate actual physiological signals. Let me know if you'd like further tweaks or additional functionality.
Yeah, I really like the idea. So that's really nice. However, there's a bit of a problem, I think, that the dichrotic notch keeps moving in a weird way. I'm pretty sure that is not correct. I'll provide a few images for your reference. But yeah, the animation of it doesn't seem to be correct. I'm pretty sure the dichrotic notches should just stay in the same place. So I like how the waveform is moving on the canvas, but then the dichrotic notch should be somehow fixed to the same spot. Yeah, if you can explain in the chat first what's happening, that would be great.
The current issue with the dichrotic notch is due to the way it is being drawn. Specifically, the notch is applied at a fixed position on the canvas based on the X% 50-20 and an X% 50-25 condition. This means the dichrotic notch effect is always tied to a specific range of X values as the waveform moves across the canvas, which causes it to appear in inconsistent locations relative to the waveform. In a real PPG signal, the dichrotic notch is a specific point that occurs consistently in the cardiac cycle, typically after the systolic peak, and it should appear fixed in phase with respect to the rest of the waveform features. In other words, the notch should stay in the same relative position on each repeating cycle of the waveform, not float around or change location with each pass of the waveform. To fix this, the notch position should be calculated based on the phase of the waveform, ensuring that it appears after each main systolic peak. The notch should always occur at the same part of each cycle, depending on the frequency, which correlates with heart rate. Instead of using the X% 50 condition, we need to calculate the phase or timing within each heartbeat. This way, we can ensure that the notch is consistently positioned after the main peak during each cycle, resulting in a more realistic and stable representation. In short, to fix the dichrotic notch: 1. Tie the notch to a fixed point in the cardiac cycle rather than to a specific pixel range. 2. Calculate the correct phase position based on the waveform frequency, so the notch is always located where it naturally occurs after the systolic peak. Would you like me to implement this fix in the code?
Yes, we're having an issue. Yeah, the implementation didn't work. So it implemented something, but then we did the bug fixing, and it
I have reviewed and fixed the code so that the dichrotic notch stays fixed in phase within each cardiac cycle, providing a more realistic representation. Let me know if you need further adjustments or additional features.
no, that doesn't work great. Can you double check? There's something wrong with the implementation. Yes, I did find a few issues. It's promising to correct the issues.
I've corrected the calculation for the dichrotic notch to ensure it stays consistent within each cardiac cycle. The notch now appears at a fixed phase point, 60% relative to each cycle, providing a more realistic and stable waveform. Let me know if you need further adjustments or more features added.
The notch location is now better. But it does not, the notch doesn't look realistic. Can you explain the edit, the image attached? Don't change the code yet, just an explanation.
The dichrotic notch currently appears as a sudden, sharp downward spike, which looks unrealistic. Here are the key reasons why it doesn't look natural. 1. Abruptness. The dichrotic notch is implemented as an immediate drop, y equals dichrotic notch intensity, making it too sudden and exaggerated. In a real PPG waveform, the dichrotic notch is a smooth dip rather than a sharp spike. 2. Width of the notch. The notch currently affects a narrow range of x values, cycle phase 0.6 and in cycle phase 0.62, which results in an overly sharp and quick feature. Real dichrotic notches are typically broader and more gradual. 3. Phase dependency. The current implementation does place the notch at the correct position in the cycle, around 60% of the cardiac cycle, but the shape of the dip lacks any smooth transition. A realistic notch should have a smooth entry and exit rather than being just a point of subtraction. To improve this, the following changes should be made. Smooth transitions. Instead of abruptly decreasing y, you could use a sinusoidal or Gaussian-like function that smoothly reduces the amplitude over a slightly longer range of the cardiac cycle. Broader notch. Increase the width of the notch to create a gradual transition. For instance, make the notch effect occur over a wider range of phases, e.g. from 0.55 to 0.65, which will create a smoother dip. Amplitude adjustment. Use a more gradual modification of y rather than a fixed value, such as scaling the reduction with a smooth function, math.cos or similar, that gradually approaches the minimum and then rises again. These adjustments will create a more natural physiological representation of the dichrotic notch, leading to a smoother and more realistic waveform.
Yes, it doesn't look very realistic at the moment. I don't want to show any copyrighted material. Can go check out how a PPG waveform should look like. Like Wikipedia or something.
I've adjusted the dichrotic notch to make it more realistic by using a cosine function for a smoother entry and exit. This approach creates a gradual dip, ensuring the notch blends more naturally with the rest of the waveform. Let me know if this looks more accurate or if further adjustments are needed.
Should the notch be happening after the peak or before the peak? Also, the direction of the notch. Can you check? Does it look correct? Or is this an inverted? Is this an inverted waveform?
The current implementation of the dichrotic notch has the following issues, based on the observed waveform. 1. Incorrect placement of the notch. The dichrotic notch is currently positioned on the ascending or descending phase of the waveform, which is not correct. In a real PPG waveform, the dichrotic notch appears after the systolic peak during the descending phase, but before the end of the descent. It usually indicates the aortic valve closing and is located within the descending part of the curve. 2. Direction of the notch. The dichrotic notch typically appears as a small dip or indentation, not as an abrupt spike. It should smoothly curve inwards rather than showing a sharp cut into the waveform. In the current implementation, the notch is effectively being rendered as an inverted peak, which is unrealistic. The direction should be a subtle inward dip that continues smoothly along the general downward trend of the waveform. Summary of required corrections. Position. The dichrotic notch should be placed after the systolic peak, ideally around 60 to 70% of the cardiac cycle, but not exactly at the peak or before it. It should appear as the waveform is descending, typically where the waveform's steepness reduces. Smoothness and direction. The notch should blend naturally with the waveform, forming a small downward dip, not an inverted spike. The current cosine-based transition is too sharp and unnatural. These improvements will make the dichrotic notch more consistent with real physiological characteristics observed in PPG waveforms. Shall I proceed with modifying the code accordingly? The current dichrotic notch effect still isn't ideal, as seen in the latest output. The notch is too abrupt and doesn't blend smoothly into the waveform, which is causing it to look artificial. Here are some issues and solutions to improve the dichrotic notch. 1. Placement issue. The dichrotic notch is still not placed perfectly after the systolic peak. The notch should appear at a point that is always after the peak, but not immediately. We should adjust the dichrotic notch placement to occur during the downward phase of the waveform. 2. Smooth transition. The notch itself should be a more subtle dip rather than an abrupt spike. This requires a softer blending function, and it needs to be applied over a slightly longer range of the phase to avoid the current cut-like appearance. 3. Amplitude calculation. Instead of directly subtracting the value for the notch, we should scale it based on the waveform's amplitude at the notch point to make it proportional. Would you like me to make these corrections directly in the code? It seems that the dichrotic notch is still not quite appearing as intended in the updated waveform, even after adjusting its position and smoothness. Here's what I notice. 1. No apparent notch. Even with the dichrotic notch intensity at 10, it's hard to distinguish the dichrotic notch. It seems either too subtle or is blending too much into the waveform, likely due to how the transition is implemented. 2. Phase width issue. The current width of the notch phase, 0.1, might still be too small to create a distinguishable notch. A slightly wider phase might help in making the notch more visible while maintaining its realistic, smooth dip. Would you like me to make these corrections to improve the notch visibility and placement? Specifically, increase the width of the dichrotic notch phase. Adjust the effect to ensure the notch appears more prominently while still looking natural. Let me know if you'd like to proceed with these adjustments.
Okay, can we still check the intensity of the notch? Seems to be too low at the moment, so even when I set it to 10 I can barely see it. And also the location of the notch seem off. It seemed just to be on top of the peak instead of after the systolic peak. Can we fix that? Can you just specify in the chat how you're gonna address it before actually changing the code?
To address the concerns with the dichrotic notch visibility and its placement. 1. Intensity adjustment. To make the dichrotic notch more visible when the intensity is at its maximum, I will increase the multiplier used to adjust the notch's amplitude. This will make the notch dip more prominent, especially at higher intensity settings. 2. Placement correction. Currently, the notch seems to be appearing on or near the peak of the waveform. This happens because the dichrotic notch starts too early relative to the peak. To correct this, I'll start the notch slightly later in the cycle to ensure it occurs after the systolic peak. The dichrotic notch should be positioned between 70 to 90% of the cardiac cycle rather than starting at 65%. This will ensure that the notch appears during the descending part of the waveform, making it physiologically accurate. Would you like me to proceed with these changes to the code? I've adjusted the dichrotic notch to start later in the cycle, between MOS 75% and 90%, ensuring it appears after the systolic peak. Additionally, I increased the intensity multiplier to make the notch more visible when set to higher values. Let me know if these changes produce the desired outcome or if more tweaks are needed.
Okay, it looks like yeah, we could move the position of the notch even a bit further away from the peak. So it should be almost in the middle between the peak and the trough. And also the direction of the notch doesn't seem correct. It currently seems positive, whereas it should be a negative notch. Can you just describe what's going on? Also look at the image provided. Just in the chat, don't modify the code yet.
The dichrotic notch is currently positioned too early in the cycle, often aligning with the systolic peak, which makes it look incorrect. It should ideally occur between the peak and the trough, which means we need to shift the starting position even further to approximately 85 strive to 90% of the cardiac cycle to ensure it falls well after the peak in the descending phase of the waveform. This change will better match the physiological timing of the dichrotic notch, which is observed after the peak pressure. Additionally, the notch's direction is currently positive, creating a bump instead of a dip. This is incorrect, as the dichrotic notch should always be a negative feature, appearing as a subtle dip in the waveform. I will update the logic to ensure the notch introduces a negative deflection instead of a positive one. Once we implement these changes, we should see the dichrotic notch appearing more accurately in its proper location and as a dip rather than a spike. Let me know if you want me to proceed with these changes. The current waveform shows improvement, but the notch still seems slightly off. Here are the observations. 1. Positioning. The notch appears a bit closer to the peak than it should be. I will adjust the start and end positions to ensure it is well within the descending phase, more like 87% to 97% of the cycle. 2. Negative deflection issue. Although we attempted to make it a negative notch, it may not be pronounced enough. I'll increase the negative multiplier to make the deflection more visible while ensuring it is clearly a downward dip rather than an ambiguous bump. Would you like me to proceed with these specific adjustments? I've updated the start and end positions of the dichrotic notch to 87% and 97% of the cycle, and increased the negative deflection multiplier to make the notch more visible and accurately positioned between the peak and trough. Let me know if this looks better or if further adjustments are needed. I've increased the negative multiplier for the dichrotic notch effect to make the notch more pronounced and ensure it appears as a negative deflection. Let me know if this adjustment looks better now.
Yeah, we're going a bit in a loop here. Looks great. We have pretty much everything we need, except that the notch is not negative as it should be. Okay, can we fix the notch direction?
I've adjusted the multiplier to ensure that the dichrotic notch results in a clearly negative deflection. The notch should now appear as a distinct dip, more in line with a realistic PPG waveform. Let me know if this looks better.
Still, the notch should be negative and not positive. Can you fix the code?
I've updated the code to ensure that the dichrotic notch has a more pronounced negative deflection. Let me know if this now appears more realistic.
Yeah, obviously you can do quite a bit, but then struggling to fix this little thing. Can you explain the code that is responsible for the direction of the notch?
The code snippet that handles the dichrotic notch, y minus equals dichrotic notch intensities to math.sin math.pi notch phase tot2 uses a negative subtraction to create the notch as a dip, but the effect might still be too subtle due to how the amplitude and sharpness are impacting it. To make the notch more clearly negative, I will further increase the negative multiplier or adjust other factors affecting amplitude, ensuring the notch is distinctly visible and properly oriented as a negative deflection. Shall I go ahead with this adjustment? I've increased the negative multiplier further to ensure a clearly visible downward deflection for the dichrotic notch, even when the intensity is set to the maximum. This adjustment should make the notch more distinct and always negative as desired. Let me know if this change brings the expected outcome.
Hey Rohan, how you going? So there might be a delay in when I receive the message and when I respond. Well, because I see it later than real time. Different definitions for real time, isn't it? Try to update this code for synthetic PPG visualizer. It's working pretty well already, but it's this funny thing with the notch, the dichrotic, not the, yeah, the dichrotic notch being positive like this instead of negative. Yeah, let me. I don't think there is a bug in the code, well, at least we're not getting any errors or anything. Might do a code review. Yeah, this notch, yeah, everything looks good. Almost too good. But yeah. Have you worked on time series data before? If yes, can you please show me your work? Show me your work. Well, this is my work. Well, kind of. It's mine, and ChatGPT should be included as an author. I mean, yeah, sorry, just trying to be a smart ass. You mean like previous research work? Yeah, I'm not sure I'm allowed to talk about it because it's now proprietary. But yeah, essentially a project I was on got acquired by big um, company, implant company. I did my PhD on cochlear implants, so you can guess what company that is. And it's currently in a clinical trial, so we're doing a lot of EEG processing for that. Therefore, most of the tools on BioniChaos.com are EEG. And yeah, by the way, we added this hearing test yesterday. That was a successful session. I haven't done like a demo of how it works. Can do it quickly now. It only takes 1 or 2 minutes. So essentially, this will be playing 50 hertz. Obviously, I can't really hear it well because my speaker would not actually produce 50 hertz. Should be able to hear 100 hertz. Can hear some weird noise. Okay, now I can hear something. So this is a 200 hertz signal. I don't know if you can hear it. Can hear something. So the idea is that now I'm getting it in the left ear, and I'll just set the threshold for when I can just hear it. So just above threshold. So I'm trying to find the threshold level. Then I get it in my right ear. Yeah, can hear something. Well, I have to actually stop talking. Yeah, can hear something there. Yeah, can hear that. You can hear. That's a good sign. I can I can test your hearing as well. Just without you actually using the tool, you can just listen to the video and you can tell me if you can hear it or not. But even better, you can just go to the link and do it yourself. Yeah, so this one. Yeah, I mean, I can try go lower. I think I can still hear something, but yeah, I can definitely hear it here. Yeah, it makes a difference if you go bottom up or top bottom in terms of that will change your threshold. And yeah, that kind of stuff is what I was doing my PhD on. Can definitely talk about that. That was quite a while ago. It will be really testing my memory. Anyhow, it will progress through the frequencies. Yeah, so I can hear it there in my left ear. Now I'm checking my right ear. Yeah, so just doing a mock-up doesn't have to be super accurate. But yeah, trying to find that threshold where you can just hear it. Can probably go a bit lower. Yeah, the other ear. It's not much longer. We're almost done. Yeah, the tones are a bit annoying as well. Yeah, and same goes with 12 kilohertz. It's also, well, it's a problem of my headphones as well. They might not be able to even produce it. I think I can hear something, but yeah, it's actually giving me headache. Like if I listen to it for too long. Yeah, I can definitely hear like a mosquito buzzing in my left and right ear. And last one is this 14K. No, I can't actually hear it. I see something actually going into the audio stream in my audio mixer, but I can't say that I can hear it myself. Anyhow, and we are done. It will tell you test complete. You can now download your audiogram. You hit that button there and you get an image of your audiogram. And that's what I did yesterday. Should be similar to what I got now. Well, yeah, the thresholds are a bit lower because I was like doing it essentially longer, trying to listen, find the threshold in a bit better way. And yes, there's an explanation of how it works. Tips for best results, obviously, quiet room, high quality headphones. Yeah, future directions. And obviously, there's a big disclaimer: this audiogram tool is intended for informational and educational purposes only and is not a substitute for a professional medical evaluation, diagnosis, or treatment. The results of this hearing test may vary based on the quality of your headphones, device settings, calibration. For an official hearing assessment, please consult a licensed audiologist or healthcare provider. So, yeah, there you go. So the link is available on the main page. Happy to pop it in the chat as well. And you can download your audiogram. Of course, yeah, we have to keep in mind that the decibel dB is not calibrated, but remember that the dB scales can be different. And essentially, in a hearing dB, can do a rapid fire with a ChatGPT. Can you quickly explain decibel levels?
Got it. The decibel levels in an audio recording indicate the loudness or intensity of the sound. In hearing tests, these levels help determine the softest sounds a person can hear at different frequencies.
So what does 0 dB hearing level means?
The 0 decibel hearing level is a reference point. It represents the quietest sound that a person with normal hearing should be able to hear at a particular frequency. It's not the absence of sound, but rather a baseline for measuring hearing ability.
So would you say this value is subjective or objective?
Hearing level measurements, including the 0 decibel level, are objective. They are based on standardized tests and equipment to measure how well someone can hear at different frequencies, regardless of personal perception. However, individual experiences of sound can be subjective, influenced by factors like attention, health, and environment.
Okay, so if I'm did a hearing test using not calibrated equipment, how good is it?
Using non-calibrated equipment for a hearing test can lead to inaccurate results. Calibration ensures that the equipment is producing sound at the correct intensity and frequency levels. Without calibration, the test might not accurately reflect your hearing ability, potentially resulting in false readings.
Like, can I calibrate? So if I don't have a very expensive calibrated equipment, can I calibrate the decibel levels to my own hearing?
While it's challenging to achieve precise calibration without professional equipment, you can perform a basic self-calibration for personal use. To do this, find a sound level meter app or device and a set of headphones known for flat frequency response. In a quiet environment, play sounds at different frequencies and volumes.
Yeah. Anyway, you get the gist. So we're essentially trying to do the same thing today. A JavaScript code for a synthetic PPG waveform visualizer. As you can see, it is working pretty well. So we have heart rate. Not sure about the heart rate. Going, yeah, the 180 beats per minute. Yeah, it depends. Well, it kind of depends what it was showing in the window. Is it transcribing all this time? Let's clear it. And let's clear it again. We did a code review. Let's see what suggestions we've got. Consider setting the canvas width and height to fixed values or dynamically adjust. Okay, the frequency calculation may lead to unexpected behavior for extremely high or low heart rates. Consider clamping the heart rate to a practical range. Okay, that sounds like a good. Aren't we doing this already? Yeah, I don't know why it's modifying the whole code instead of just the relevant bit. I don't see much difference. Yeah, that peak, that notch is still positive. It has to be negative. I thought it would be an easy fix, but and what are the chances that I'll be able to fix it myself? Hey, can you in the chat alone, without modifying the code, ask some questions and invite the viewers to join in the conversation? Just in the chat.
All right, let's take a moment to chat about what we see in the current Pulse Vision setup. We've got controls for heart rate, oxygen saturation, waveform sharpness, noise level, and dichrotic notch intensity, all influencing the waveform in real time. The waveform itself is generated using JavaScript, giving us that interactive visualization. Now I'm curious, what do you think of how the waveform looks when adjusting the dichrotic notch? Does it appear as realistic as you'd expect for a PPG reading, or are there aspects you'd tweak further? And when you change the noise level, does it add a level of variability that feels natural to you? I'd love for everyone watching to jump in with their thoughts. What features would you add to make this visualization even better? Or what might help make it more educational or fun for users who are new to biomedical signals? Feel free to share your ideas and join the conversation.
Now the other main question is that ready to be published. Well, not quite yet, because that mainly because that diacritic notch is still appearing positive instead of negative, so it should be deflecting downwards instead of upwards. Can we just fix that bit? That should be an easy fix, is it? Oh, I didn't quite. The diacritic notch is still facing upwards. Can we make sure it is a negative notch? So the curve should be going down instead of up.
I've adjusted the direction of the dichrotic notch so that it now creates a negative dip in the waveform, as expected. Let me know if it looks more accurate now.
Yay! It actually fixed it. Good job. Thank you very much. So now it looks much more realistic. Yeah, there's obviously a few more things that we can fix, but looks great as it is. Still had a few suggestions in the code review.
I'm glad the fix worked, and the dichrotic notch now looks realistic. It's great to hear that the waveform is more visually accurate. If you'd like to continue making smaller refinements or add more interactive features, like additional annotations, an adjustable pulse amplitude, or even overlay comparisons, let me know. And for everyone watching or reading along, we're always open to feedback and ideas. What features would make this visualization more engaging or educational for you? Share your thoughts, and let's make Pulse Vision the best it can be. Sure. Let's take a broader view of Pulse Vision and break it down a bit more for everyone tuning in. Overview of Pulse Vision. Pulse Vision is an interactive web-based visualizer that lets users generate and manipulate synth-PPG, photoplethysmography waveforms. PPG is commonly used in medical devices, like pulse oximeters, to measure the rate of blood flow and the oxygen levels in the body. The visualizer includes several controls: heart rate, BPM. Users can adjust the heart rate using a slider, ranging from 40 to 180 beats per minute. Oxygen saturation, percent. This slider lets users change the oxygen saturation between 85% and 100%, which impacts the overall amplitude of the waveform. Waveform sharpness. This control changes the sharpness of the PPG waveform, which influences how pronounced the peaks and valleys appear. Noise level. The slider here controls the variability of the waveform, simulating the kind of noise or interference that can occur during real-life measurements. Dichrotic notch intensity. This slider controls the dichrotic notch, a small deflection that appears after the main peak. The recent fix we made now ensures that the dichrotic notch is a negative deflection, as expected in a real PPG signal. All these controls help users understand how various physiological factors affect the PPG waveform, providing an educational yet fun interface for learning about biomedical signals. Questions for the audience. 1. How realistic does the waveform look? With the dichrotic notch fix and adjustable noise levels, do you feel the waveform looks realistic enough to mimic actual PPG readings? If not, what specific features do you think could be improved to enhance its realism? 2. Additional features you'd like to see? Are there any other physiological factors that we could add controls for? For example, would adjusting the blood pressure or adding skin tone effects make the visualization more insightful? 3. User experience and controls. Is the current set of sliders intuitive, or would you like to see different types of controls, e.g., buttons or preset options for conditions like exercise or rest? How might we make it easier for a general audience to engage with the data? 4. Educational usage. How do you envision using this tool? Could it help teach students or medical trainees about cardiovascular dynamics? Are there features that could make it more effective in an educational setting, like annotations or pulse rate readings over time? 5. Visual styling. What do you think about the visual style of the waveform and interface? Does the color, size, or responsiveness fit well for understanding and engaging with the data? Would you like to see a feature that overlays real PPG data for comparison? Feel free to share your thoughts and ideas on how we can take Pulse Vision even further. Whether it's new features, styling improvements, or use cases we haven't considered yet, every bit of feedback helps us create an even more engaging and educational tool.
It was a good suggestion there about something might be distorting the waveform.
Looking at the current image of Pulse Vision, we can see a synthetic PPG waveform with some distinctive features, such as sharp peaks and a noticeable notch following each main peak. Here are a few things to break down from what we're observing. Image overview. 1. Heart rate at 167 BPM. The heart rate slider is currently set to 167 beats per minute, which results in a fairly rapid waveform on the canvas. This high heart rate makes the peaks appear closer together, as expected. 2. Noise level and sharpness effects. The noise level is set to 5 and waveform sharpness is at 8, giving the waveform a rugged and quite erratic appearance. The sharpness also enhances the angles of the peaks, making the waveform more pointy compared to smoother, idealized PPG signals. 3. Dichrotic notch. The dichrotic notch intensity is set to 8, making the notch after the systolic peak more pronounced. However, with the high noise level and sharpness, it can be a bit challenging to distinguish clearly. Technical questions. 1. Effect of noise and sharpness combination. How does the interaction between the noise level and waveform sharpness affect the overall readability of the waveform? For instance, is the current setting making it harder to distinguish between physiological features such as the dichrotic notch and the main peak? Would reducing the sharpness while keeping the noise level constant help in making the waveform more representative of a real PPG signal? 2. Waveform fidelity. With a high heart rate, the waveform is generated more frequently. Are there any noticeable discrepancies in the sinusoidal generation that could be attributed to aliasing or drawing speed limitations? Considering the dichrotic notch's position, do you think the current implementation accurately reflects the literature for notch placement in high-frequency heart rates? 3. Amplitude scaling and noise influence. The amplitude of the waveform is affected by the oxygen saturation level, set here at 97%. At this high value, the amplitude is near its maximum, and combined with noise, the waveform can look more chaotic. Could we consider adding an additional filter to smooth out the noise while retaining the physiological features? If we reduce the noise level to 1, how would that change the visibility of the dichrotic notch? 4. Educational usability. Given the current settings, do you think the visual output would be helpful for someone trying to learn about PPG signals? Would adding an overlay of an ideal waveform help users see the difference between physiological variability and artificial noise? What about adding a real-time text annotation that explains why each feature, e.g., the dichrotic notch, is appearing where it does? Would that enhance the educational value of the visualizer? These questions aim to refine the current implementation by balancing realism with interactivity, keeping educational value at the forefront. I'm curious about your thoughts and ideas on how to address these, and any feedback from viewers is also very welcome. I've normalized the sharpness factor to avoid distortion, which should help maintain a more realistic waveform appearance. Let me know if there's anything else you'd like to tweak or if you want further enhancements to the visualization. I've made adjustments to ensure that the dichrotic notch now has a negative deflection by modifying the calculation for the notch. Let me know if there's anything else you'd like to adjust or further refine in the waveform visualization.
Okay, so we want to publish this. So we take the currently working code. Hey, can you open a new canvas code canvas window? Okay, we'll put this code in. Okay, let's explain the code quickly. Yeah, now before we can publish this, Yeah, we don't have the navigation bar on the website anymore. So just simplify things. Yes, we have this color scheme that we are trying to be consistent about. Yeah, we'll have embeddings. We have embeddings of the YouTube videos on the page. We have to actually update. Yeah, I think that's the new navigation. Simple. Yeah, so this is the end of style CSS. The CSS, this CSS is for the entire BioniChaos website. Each page on the site can have its own styling. Can have its own styling embedded in the HTML. So what will happen if I just pop this in? The HTML file represents the PPG. What? Okay, we obviously didn't take that prompt into account. So what I was trying to say so this is the CSS for the entire page. In the specific HTML file. Okay, so the prompt for this is we have styling for the whole website that we use that is applied to every page on the website. But every specific page, like the one we are currently working on, should have its own specific styling just embedded inside the HTML. How does that sound?
That sounds like a well-organized approach to maintaining your website's styles. By keeping a main global style sheet, /styles.cs, for the common design elements, you ensure consistency across all pages, giving users a uniform experience in terms of fonts, colors, and overall design language. At the same time, adding page-specific styles directly inside the HTML of each page allows for quick and easy adjustments that only affect that specific page. This is particularly useful when individual pages need unique styles or experimental features without cluttering the main CSS file, which helps maintain code cleanliness and avoids unexpected conflicts. For instance, embedding a style tag directly in your HTML to define styles specific to the Pulse Vision page makes it easy to fine-tune elements like sliders, waveform colors, and any unique design features that don't apply to other pages. Here is an example. HTML head link or style sheet styles.c / page specific styling for Pulse Vision. App container var miradors 2-10 border 1px.
Okay, so can we update the specific code at hand? Just keep the relevant styling that we do not have in the global CSS file. And link to the global CSS file as well.
I've updated the code to link the global CSS file and kept only the page-specific styles embedded within the HTML. Let me know if you need further adjustments or if you'd like to add more unique styles for this page.
Can we remove the app container? We don't really need it. Hey, can we remove the footer as well? We don't need it. Also, can we fix the sliders, make them look better? Can we fix the sliders, make them look better? Also, we changed the width of the PPG canvas to 90%, but also can we make sure it's appearing in the horizontal center? And in terms of the height, can we make it about half the visual window size? Half the screen.
I've removed the footer, updated the sliders to have a more modern and polished look, and adjusted the canvas to be horizontally centered with a width of 90% and a height set to half the screen. Let me know if there's anything else you'd like to adjust.
Yes, so you can have 150 lines of code, which is quite a bit. There's something. Yes, something that I don't particularly like with. Can you explain what's with the current window size? How many seconds are we displaying? Shall we display about 10 seconds? Can you just explain which code, which bit of the code I should modify without actually modifying the code?
To display around 10 seconds of the waveform, you should adjust the frequency and the time progression within the draw waveform function. Here are the specific parts of the code that you may need to modify. 1. Frequency calculation, frequency. The variable frequency is currently calculated as heart rate 60, which determines the frequency of the waveform based on the heart rate. To display a 10-second waveform, you need to ensure that the value for frequency appropriately represents the duration you want to display. You could adjust the calculation of frequency to factor in the desired time frame. 2. Time progression. Time. The line time plus 0.05 determines how fast the waveform progresses across the canvas. To control how much of the waveform is visible within the 10-second period, you may need to adjust this increment. A smaller increment will result in slower progression, thereby displaying more of the waveform over time. By modifying these two parts of the code, frequency and time, you can adjust the visual duration of the waveform to approximately 10 seconds. If you need more precise control over this duration, you may also consider adjusting the cycle length calculation to better fit your requirement.
No, we want to keep everything as is. It's working pretty well. All I'm asking is what is the current window size? So for example, when the beats per minute is 100, I see roughly 2 cycles. So can you specify what's the current window size? Just in the chat. Don't modify the code yet.
In the current setup, the window size, in terms of how much time is being displayed on the canvas, is determined by several factors. 1. Frequency calculation. The variable frequency is calculated as heart rate 60. This essentially converts heartbeats per minute into beats per second. For a heart rate of 100 BPM, frequency becomes approximately 1.67 hertz, which means 1.67 cycles per second. 2. Cycle length. The cycle length is calculated as canvas.width/frequency. This means the number of pixels needed for a single cycle is inversely proportional to the frequency. Given that canvas.width is fixed to 90% of the available window width, and depending on the value of frequency, the number of cycles visible will vary. 3. Time progression. The time variable is incremented by 0.05 per frame, time plus equals 0.05. This determines how quickly the waveform progresses across the canvas and indirectly affects the apparent window size in terms of how many seconds are displayed at a given time. Since you see roughly 2 cycles at a heart rate of 100 BPM, it means that the window is showing about 1.2 seconds of the waveform, since at 100 BPM, frequency is about 1.67 hertz, and you see roughly 2 cycles. To adjust this window size, you could 1. Increase or decrease the time increment to make the waveform move faster or slower across the canvas. 2. Adjust frequency or cycle length if you want to increase the number of cycles visible within the canvas width. Currently, based on the frequency and time increment, the window size is roughly designed to display around 1 to 2 seconds of waveform data. To display 10 seconds worth of data in the canvas, you should make the following adjustments. 1. Cycle length. Cycle length. The current cycle length is calculated as canvas.width/frequency. This essentially means that the canvas width determines how much of the waveform is visible, and the frequency value is dependent on the heart rate. To show 10 seconds of data, you need to make sure that cycle length is calculated in such a way that the canvas width accommodates 10 seconds of the waveform. You may need to adjust cycle length to represent a longer time period, taking into account the desired 10-second duration. Number 2. Time increment. Time plus 0.005. The time progression is controlled by time plus 0.05. This value affects how quickly the waveform moves across the canvas. To display 10 seconds worth of data, consider reducing the increment to make the waveform move slower, allowing for a longer visible time window within the canvas. You may need to adjust this increment to balance the speed and ensure that approximately 10 seconds of data fits on the canvas. 3. Canvas width and frequency. Given that you are seeing roughly 2 cycles at 100 BPM, the effective time window currently is about 1.2 seconds. To extend this to 10 seconds, you could adjust either the canvas.width or modify how the frequency relates to the display duration. One approach is to make frequency dependent on both the heart rate and a factor that accounts for the total time window, in this case, 10 seconds. In essence, focus on adjusting the cycle length to ensure that it represents tahuas 10 seconds of cycles, and modify the time increment to adjust the visual scrolling speed appropriately. Currently, the window size, i.e., the portion of the waveform displayed on the canvas, is primarily determined by the cycle length, frequency, and time increment. Here's a breakdown of the relevant pieces of code that determine the visual duration. 1. Cycle length calculation. JavaScript const cycle length equals canvas.width frequency 0.4. Full cycle length in pixels. The cycle length is calculated based on the width of the canvas divided by the frequency, with an extra multiplier of 0.4 applied. This line dictates how many pixels represent one full cycle of the waveform. The 0.4 multiplier effectively shrinks the length of each cycle, thereby determining how many cycles fit within the visible width of the canvas. 2. Frequency calculation. JavaScript const frequency equals clamped heart rate /60. The frequency is derived from the heart rate and essentially represents the number of cycles per second in hertz. For a heart rate of 100 BPM, the frequency would be 160 equals 1.67 hertz. This means there are about 1.67 cycles per second. 3. Time increment. JavaScript time plus 0.05, the time variable controls the horizontal movement of the waveform across the canvas. Incrementing time by 0.05 determines how quickly the waveform moves and affects the apparent window size by dictating the speed at which the waveform advances. 4. Overall window duration. Given that the canvas width and frequency dictate the number of cycles visible at a given moment, the current window size, how many seconds of data are displayed, can be approximated by how long it takes for the waveform to scroll completely across the canvas. At 100 BPM, 1.67 Hz, and seeing approximately 2 cycles, The effective window size is about 1.2 seconds. This means the current setup displays around 1 to 1.5 seconds of the waveform at a time, depending on the heart rate. To adjust the window size to display 10 seconds worth of data, you would need to modify 1. Cycle length multiplier, 0.4. Increase this value so that the canvas can fit more cycles, effectively extending the window duration. 2. Time increment, time plus 0.05. Reduce this increment so that the waveform moves more. Questions for clarification. Continued. 1. Cycle length and frequency. Currently, the cycle length is calculated as canvas.width/frequency 0.4. The 0.4 multiplier reduces the cycle length and makes more cycles visible in the canvas. Would you like more cycles to be visible at once, or would you prefer a smoother, stretched out waveform to give a more relaxed view? 2. Waveform complexity. The sharpness factor, math-pow, math-sin2, math-pi cycle phase, waveform sharpness, influences how peaked or smooth each wave cycle looks. Does the current sharpness slider meet your requirements for demonstrating waveform features, or should the effect be more exaggerated? 3. Noise implementation. Noise is added as math.random-0.5 noise level to add variability to the waveform. This randomness simulates real-world imperfections in PPG signals. Would you like to adjust the noise to make it more pronounced or keep it as subtle as it currently is? 4. Dichrotic notch. The dichrotic notch is a key feature of the PPG waveform, especially for identifying cardiovascular health aspects. Right now, the notch effect is applied using a sine modulation with a fixed start and end, dichrotic notch start and dichrotic notch end. Do these notch settings look appropriate in the waveform, or would you like to fine-tune their positions and intensity further? 5. Time increment, time plus 0.05. The time variable is incremented by 0.05, which controls the speed at which the waveform moves across the canvas. To display 10 seconds of waveform data more effectively, this increment could be reduced to slow down the scrolling speed. Are you happy with the current scrolling rate, or do you want it to be slower to match a specific time frame? 6. Heart rate and visible cycles. At a heart rate of 100 BPM, you currently see about 2 cycles in the canvas. To display 10 seconds worth of data, should we increase the canvas width to hold more of the waveform at once? Decrease the time increment, time equals 0.05? Modify cycle length to better distribute cycles across the canvas? 7. User experience enhancements. Should the labels, such as heart rate or oxygen saturation, have more details or be tooltips that explain their significance, especially for users unfamiliar with PPG data? Would you prefer to add a pause button to allow users to stop the waveform and analyze specific details? The bigger picture. The Pulse Vision app aims to offer an interactive visualization of synthetic PPG signals, giving users insight into how heart rate and other physiological parameters influence PPG waveforms. This type of tool can be used for educational, research, or training purposes, allowing users to better understand cardiovascular metrics through visual exploration. Key considerations for future development. 1. User-friendly features. Consider adding predefined presets for different heart conditions. For example, preset options for conditions like tachycardia, bradycardia, or hypoxia would allow users to explore and understand what these signals look like under different physiological circumstances. Adding a snapshot feature that allows users to capture the current waveform as an image or data file would enhance the value of the tool for education and research purposes. 2. Extending the visualization. Currently, the canvas displays around 1 to 2 seconds of waveform at a time. Extending this window to 10 seconds will make it easier for users to spot trends and understand the impact of changing parameters over a longer duration. You could also consider dynamic scaling, where the number of cycles displayed adjusts based on the selected heart rate, making it more intuitive for users to understand changes in real time. 3. Parameter simulation. Adding sliders for additional parameters, like respiration rate, blood pressure, or vascular resistance, could make the simulation more comprehensive and educational. This would allow users to see how other physiological factors can affect PPG readings. The goal is to ensure Pulse Vision offers both an engaging user experience and a scientifically meaningful representation of cardiovascular health. Would you like to discuss any specific features further or explore a new direction for improving the application?
Hey, can we also provide the instructions? So essentially, can we expand the overview to provide the instructions as to how to use the web application, particularly going over each of the sliders, what do they mean, and what to expect when changing them? Also add a section on future directions. Can we also somehow fix the way the sliders appear? They currently a bit disordered. Disordered. They're a bit messy at the moment. The sliders are a bit messy. Can we change the styling for them to just organize it perhaps into two separate sections? Which microphone am I using? It's crazy. Cannot get what I'm saying. Can we change the styling for the slider controllers? Okay, we have an overview section. Okay, we have general view. Yeah, we don't need that to be repeated, do we? Okay, we have general overview instructions. We have each slider explained. And future directions. That sounds very good.
I've updated the styling for the sliders to give them a more polished look. The sliders now have a thicker track, rounded thumb, and a subtle shadow for better visual appearance. Let me know if there's anything else you'd like to adjust.
I don't think I like this one. It always tends to overdo on the styling front. Yeah. No, like a simple styling. We just want to make sure it's organized in a better way.
I've organized the sliders into two groups using a control group container to split the controls into two sections for better layout. Let me know if you need further modifications or styling adjustments.
Okay, I do like the controls in two columns. That's fine. But can we just make sure each control is in the new line? So they organize better. See image attached. There's some, what that bit? There's a bit missing there. Yeah, there's some sort of bug in the canvas. Um, okay, this is better, but do we need that control group section? I don't think so. Yeah, there's something weird started happening there as well, with the waveform sharpness. Don't think. A noise level can be about 5 for default. A notch intensity. This doesn't have to be in the new line. Oh, come on. There's too many new lines. manually remove those, and that's a bit better. Which one? What's flex one? Anyway, it doesn't seem like we need those, but that's okay. I think it's looking pretty good. We can publish, and because it's JavaScript and HTML, we can essentially publish straight away. It's not a Flask application. We're actually considering placing Flask applications onto another website. Well, because it requires more electricity and stuff, so then we'll have a login for it as well. Yeah, there's something funny. What? Um, if I copy the code, what are the changes? Is it doing anything? No. Just get really confused by me pasting the code into. Okay, I might need to refresh this window. Okay, I only have the one canvas. Did it just stop working? Okay, added 5 comments. I don't see them. I know I do see them. Consider making line width dynamic or adjustable based on the user input. You can make it a bit thicker, but should be fine. We're not changing that. Might help to add mechanism to pause or stop the animation. No. Hard code at 0.4. Yeah, we put that magic number in just to have more waveforms appear. Yeah. Why? Wait. It's not in the right location in the code. Yeah, it's a bit weird. I don't think it really likes when you copy pasting code into this canvas thing. Um, okay, okay, can you start the code canvas? This is a bit silly. I don't know how to work with this thing. Okay, we have a new canvas. Explain the code. Seems like you need to start fresh every time you're doing something else, but we progress quite a bit. Um, could port this into Python or something. What? Huh. How many lines do we have? It's like just 248. No, that's fine. There's no content. It doesn't see this code, which is totally bizarre. Yeah. Looks like, yeah, I don't know how it works. Explain. Okay, now it's working. Yeah, I have to click enter in the editor, like start a new line. And now it's actually doing it. Google Ads. Yeah, we do have Google Ads, but that's, yeah, ignore that. We have the description and everything. What else did we need to do? Do you have any suggestions as to how to improve this code before we actually publishing it on our website? Importantly, we have a global styling for the whole website that we are using. I'll copy paste it below in this prompt for your reference. Did I ask you to what? What? I haven't seen it doing this before. Just added a bunch of comments. Yeah, consider moving the inline CSS to the global style sheet. Well, no, because those components are specific to this page. What else? No, that should be fine. Get rid of that. Consider making these values adjustable through additional user controls to provide more customization for the waveform visualization. So that's the position, the start and end position for the notch. That could be interesting, but yeah, let me know what you think. Should we add more controllers, or is this already enough variables to play with, or do you want more variables? Yes, the start and end position of the dichrotic notch it could make sense. Maybe you can explain, maybe you can just place it in future directions at the bottom of the page. You can just explain in the chat the pros and cons of having another two control sliders in the application. Yeah, that would be nice. We actually have our own color scheme. Let's just change the specific line of code instead of changing everything. I don't know why it does that.
The suggestion to add additional control sliders for the start and end positions of the dichrotic notch can enhance the realism and customizability of the PPG waveform. Let's explore the pros and cons of adding these new controls. Pros. 1. More realistic simulation. By giving users the ability to fine-tune the start and end positions of the dichrotic notch, the application can offer a more accurate and personalized PPG waveform, which is beneficial for both educational and research purposes. 2. Greater user engagement. Adding more controls can make the application more engaging for users, especially those with a deep interest in cardiovascular physiology. They will have more options to experiment and visualize different waveform characteristics. 3. Tailored scenarios. Users can create specific PPG signals that represent different physiological or pathological conditions. This could be useful for users trying to mimic certain patient scenarios, such as altered dichrotic notch positions due to disease or intervention. Cons? 1. User complexity. Adding more sliders can make the user interface overwhelming, especially for those who are unfamiliar with PPG waveform analysis. It's important to find the right balance between offering options and keeping the interface simple. 2. Potential for confusion. Users who are not well versed in the concept of a dichrotic notch might find it challenging to understand how changing its position affects the waveform. This could lead to confusion unless well-documented explanations are provided. 3. Space constraints. Adding additional sliders means the control panel will take up more space on the page. This could lead to a less clean design, especially on smaller screens. Recommendations. Include as future enhancements. For now, it might be a good idea to list the additional sliders for the dichrotic notch position as potential future enhancements. This will let you assess user feedback on the current version and add the features if users seem interested in more detailed control. User testing. If you do decide to add these controls, consider conducting a small round of user testing to see if they find the new sliders useful and intuitive. This feedback can guide further UI/UX improvements. Tooltips and documentation. If implemented, add tooltips or a brief information section explaining what the sliders do and their impact on the waveform. This will help minimize confusion for users who are not familiar with the dichrotic notch. Incorporation into the web application. If you decide to proceed with adding the sliders, you can place the new control for the start and end positions of the dichrotic notch below the existing dichrotic notch intensity slider. This will provide a logical grouping of all the dichrotic notch-related settings in one place. Would you like to proceed with adding these new sliders to the UI, or should we keep them as part of the future development list for now? I can help you implement either of these paths.
something wrong with that sharpness a bit. Every even numbers are doing this negative deflection. I think the deflection meant to be positive. We'll have to fix it another time, otherwise it looks pretty good. Only spend just under just under 3 hours making this. So let me know if it's useful or not. And what can be improved. Yeah, I'll finish with the robot will finish the stream for us. Just one last thing before I forget. Yeah, we could improve a few things. And let's just quickly finish that off. Okay, we'll use this image. Pulse width. We're exporting as PNG. No, JPEG. JPEG should be better, I'm not sure. Oh, that's what we use, so. And in a project, actually have a static folder. Pop that pulse width in it. Copy relative path. Let's open this in the server. This is just running locally. You won't see that update yet. A lazy loading is fine. Responsive image, heart rate, a visualization. Okay, we need a different description for it. A pulse wave heart rate, a visualization, and we had this description for it. Yep, pulse vision is a pulse vis. Is a synthetic PPG waveform visualizer that allows you to adjust heart rate, oxygen saturation, waveform sharpness, noise level, and necrotic notch intensity. That sounds like it. This is what it looks like. We'll eventually have a video on the page as well of me using it. We'll probably record it next time. When we work on something else, we'll do a overview of what we did before. It's kind of the plan. That's what we did today for for the hearing test. We need to deploy again. Right, we have the pulses. Oh, forgot one thing. Forgot that image. That image. Yep, we have the image. And we need to deploy again. And we need to deploy again. And we'll share it straight away because I can't be bothered doing social media. So
Conversation Summary and Web Application Overview. In this conversation, we focused on refining and enhancing the Pulse Vision web application, which visualizes synthetic photoplethysmogram (PPG) waveforms. This tool allows users to interactively manipulate several cardiovascular parameters such as heart rate, oxygen saturation, waveform sharpness, noise level, and dichrotic notch intensity using sliders. The changes are reflected in real time on a canvas element that displays the PPG waveform. Key enhancements and changes made. 1. Slider width automation. We adjusted the slider elements to have dynamic widths that adapt to their container, improving the responsiveness and uniform look of the interface. 2. Canvas resizing fix. A bug related to resizing the canvas dynamically was resolved by adding a function that properly adjusts the canvas dimensions on window resize. 3. Styling adjustments. We ensured that the color of certain components, such as the waveform stroke, is consistently controlled using global variables from the style sheet. 4. Future directions added. We added an entry to the Future Directions section suggesting additional sliders for dichrotic notch start and end positions to assess user interest and potentially add these features later based on feedback. Overview of the web application. Pulse Vision is an interactive educational tool that helps users visualize and understand PPG signals. Users can change parameters like heart rate, adjust the rate of waveform cycles; oxygen saturation, modify the amplitude of the waveform; waveform sharpness, control how pointed or rounded the waveform peaks are; noise level, simulate real-world signal imperfections; dichrotic notch intensity, adjust the prominence of the dichrotic notch, a secondary deflection seen in PPG signals. Future improvements could include new physiological parameters, e.g. respiratory rate, options to save or export waveforms, and preset waveform conditions representing various cardiovascular states like tachycardia or hypoxia. Questions you might want to ask. 1. Are there any additional features that could enhance user interaction or educational value? For example, would adding respiratory rate sliders be of interest? 2. Would it be useful to add a feature allowing users to save or download the visualized waveform data for further study or analysis? 3. Is the current level of detail for the dichrotic notch control sufficient, or should we include more parameters for fine-tuning? 4. Should we simplify or add tooltips to help novice users better understand the impact of each slider? These questions can guide future discussions on improving the app and user experience. Let me know if you have any specific preferences or new ideas. All right, everyone. That's a wrap for today. We've successfully finished developing the Pulse Vision web application, and it's now up and running on the website. Feel free to go and check it out at bionichaos.com/pulseviz/.coms/pulseviz. You can play around with the sliders and explore how different cardiovascular parameters affect the PPG waveform. Thank you for tuning in and being part of the development process. We appreciate all your feedback and support. Don't forget to like, subscribe, and let us know your thoughts. Until next time, bye-bye and take care. Signing off.
Bye.